High School Mathematics, Calculus 1. Unit 1, Limits and Continuity of Functions. Section 1, the limit of a function. This is the first lesson for this unit. Here, we will cover the concept, definition, meaning, and notation of limits. First, let's go over the variables and symbols we'll be using. The letters at the beginning of the lowercase alphabet are typically used to represent constants. The letters at the end of the lowercase alphabet are typically used to represent variables. Greek letters are also used. Among the uppercase Greek letters, delta is used. Among the lowercase Greek letters, alpha, beta, delta, and epsilon are used. These letters are mostly used to represent constants. First, let's explore the intuitive concept of a limit. Consider the function y equals x squared. Imagine the value of x gradually approaching 1, starting from 0. The key point here is that it only approaches 1, but never actually equals 1. Since y is the square of x, it will also gradually approach 1. However, y also never actually equals 1. This time, imagine the value of x gradually approaching 1, starting from 2. Here too, x only approaches 1, but never equals 1. Since y is the square of x, it will also gradually approach 1. However, y also never equals 1. Let's look at the formal definition of a limit. In a function f(x), as the value of x approaches a, indefinitely without equaling a and the value of f(x) gets arbitrarily close to a single constant value, L. We define that the function f(x) converges to L. In this case, L is called the limit value, or simply the limit, of f(x) as x approaches a. Let's see how limits are noted. We can write the limit of f(x) as x approaches a equals L. Or, alternatively, f(x) approaches L as x approaches a. For example, for the function y equals x squared, we state that the limit of f(x) as x approaches 1 is 1. Or, we say that f(x) approaches 1 as x approaches 1. Meaning of a limit. Let's reflect on the true meaning of this notation. Saying f(x) approaches L as x approaches a means that x is infinitesimally close to a, but is explicitly not equal to a, and it implies that f(x) is extremely close to L, but f(x) does not have to equal L. For example, for the function y equals x squared, when f(x) approaches 1, as x approaches 1, it means x is very close to 1 but not 1. And f(x) is very close to 1, but not exactly 1. Going back to our example of the function y equals x squared. Let's consider the case where x and f(x) both approach 1 from the left. From a distance, it appears as though x and f(x) successfully arrive at 1. But if we zoom in closely on this behavior, we see that neither x nor f(x) can ever actually touch 1. There is a tiny margin of delta for the x value, and a margin of epsilon for the f(x) value. Approaching from the right is no different. From a macroscopic view, x and f(x) seem to reach 1. But when zoomed in, neither x nor fx can ever actually hit 1. A margin of delta exists for the x value, and a margin of epsilon exists for the fx value. This time, let's isolate our focus onto fx. Let's define epsilon as the difference between the limit value and the actual function value of fx. Let's revisit the phrasing used in the definition of a limit. The word that really stands out here is infinitely. Let's track epsilon while keeping the weight of this word, infinitely, in mind. If fx reaches 0.9, then epsilon, the margin from the limit, is 0.1. If fx reaches 0.99, that margin drops to 0.01. If fx reaches 0.999, the margin becomes 0.001. Since these are still far too large to count as infinitely, we repeat this process infinitely. If we do this infinitely, what will the difference eventually become? Surprisingly, the difference converges exactly to 0. As you know, 1/3 is equal to 0.333. Repeating infinitely. If we multiply both sides of this equation by 3, we prove that 1 and 0.999, repeating infinitely, are mathematically the exact same value. From this, one might try to find an fx value satisfying infinitely, like a number where 0.999 repeats forever, but the hypothetical last digit is an 8. However, we can never calculate the exact difference between this number and the limit, because it's impossible to count how many 9s repeat in the middle. In other words, obsessing over the literal phrase infinitely traps us in a paradox, making us question if limits can even be applied in real-world science. So, let's look at limits from a more practical standpoint. Let's consider the function fx equals x plus 1, as x approaches 1 and fx approaches 2. For instance, let's pick 3 test values. If fx reaches 1.997, its distance from the limit is 0.003. If fx reaches 1.998, the distance drops to 0.002. If fx reaches 1.999, the distance is just 0.001. Yet, these values are still far too coarse to discuss a rigorous limit. But what happens if we force these epsilon values to be significantly smaller? Let's shrink the error margin down to less than 10 to the minus 8. A threshold of 10 to the minus 8 is remarkably tight, making it perfectly reasonable to approximate fx as 2. Likewise, 10 to the minus 9 is also sufficiently small, allowing fx to be safely approximated as 2. Choosing between 10 to the minus 8 and 10 to the minus 9 is entirely an engineering decision. For calculations requiring extreme scientific precision, we can push it to 10 to the minus 10. Ultimately, it's not about a single, absolute, infinitely small epsilon being the only answer. In modern engineering and precision science, limits are computed using tolerance thresholds between 10 to the minus 8 and 10 to the minus 10. In summary, evaluating a limit is a matter of tracking values within an epsilon bound determined by practical necessity. If we set that boundary at 10 to the minus 10, any value smaller than 10 to the minus 10 will be truncated or discarded. Thus, through this minute change, the function value transitions into its evaluation limit.